Hello students, welcome to the channel. In this video, we are going to talk about isomerism in coordination compounds. Basically, this topic is from grade 12 syllabus and it is also helpful in mains and NEET preparation. Let's get started without any more delay. Isomerism, we also have learnt the very similar topic in organic chemistry. But then the isomerism that you're going to learn over here in inorganic chemistry is entirely different. So don't try and merge both of them. Try to keep them separate so that you're not confused. Let's get started. The definition of the term isomerism. What exactly is meant by the term isomerism? Isomerism in coordination compounds is a phenomena in which you have one complex or one molecular formula being represented in different structural manners. If you have one formula being able to be represented in different structures, you call it as isomerism. You call the phenomena as isomerism. So these different structures that you're drawing are called as isomers. So isomerism is a phenomena in which one formula is being represented in different structures, and these different structures that you're drawing are called as isomers. Basically, there are different types of isomers possible. So let us write a classification for this isomerism. Isomerism in coordination compounds can be basically classified into two types. The first one is structural isomerism and the second one is stereoisomerism. Structural isomerism is a kind of 2D, two-dimensional isomerism, and this deals with writing or drawing the structure on the paper. And stereoisomerism deals with a three-dimensional arrangement of the groups around the central atom. So the structural isomerism is further classified into four types. There are four types of structural isomers possible, of which the first one is linkage isomerism. The second one is coordination isomerism. The third one is ionization isomerism, and the fourth one is solvate isomerism. This fourth one can also be called as hydrate isomerism. So these are the four types of structural isomerism that are possibly observed in coordination compounds. And the next one, stereoisomerism, which is a kind of three-dimensional isomerism which deals with three-dimensional arrangement of the groups around a central atom, can be further classified into two types, of which the first one is geometrical isomerism, and the next one, the second one over here, is optical isomerism. So this geometrical isomerism is further classified based on what kind of complex are you dealing with. The first type over here is cis-trans isomerism and the second type is fake-mer isomerism. You can also call it as facial meridional isomerism. Anyway, we'll talk about the definitions of these all types of isomerisms with examples in the further pages. But before we could go there, I hope this page is clear with all of you. In case of any doubts, you can always ask me in the comment section below. Now let's get started with the structural isomerism. So structural isomerism is classified further into four types. Let's talk about them one after other. But before that, you always keep one point in mind. Structural isomerism basically is about the structural representation of the molecule of the complex in two dimensions. Over here, we don't talk about above the plane, below the plane, on the plane concepts. We only talk about the bonds and the position of the primary valency or the secondary valency or the central atoms, right? So let's move on with the first type of structural isomerism. Let's get started with coordination isomerism. While you have studied the terminology required for this chapter, you might have come across with the term called coordination sphere or coordination entity. So basically this coordination sphere or coordination entity deals with the composition of the complex present within these square brackets. So what do you have within the square bracket is what is coordination sphere. So over here in coordination isomerism, the composition of the entities present in the square brackets will vary. Let's take an example to understand this in a simple manner. So observe the first example that you see here. You're talking about a cobalt complex and there are totally 6 ligands over here. There are 6 ammonia groups and these 6 ammonia groups are 6 ligands. They act as ligands, isn't it? And there is another complex represented right next to it. It's a chromium complex and over here you are having oxalate C2O4 acting as a ligand and there are 3 ligands, right? So you observed complex number 1 and you observed complex number 2. And now you observe the second set of examples that you see here. You're talking about a complex where cobalt is acting as a central atom, but then here the ligand is C2O4, oxalate. And you have a complex in which chromium is acting as a central atom, and the ligands are ammonia ligands over here. What difference do you find between set 1 and set 2? What difference do you find between the examples that you see here in set 1 and set 2? In both the cases, the central atom that you're talking about is same. And the ligands that you're talking about is also same. Then what is the difference? The only difference is the position of the ligands and central atom is different. As in set 1, you were having cobalt and ammonia making a complex. But in set 2, you are having cobalt and oxalate making a complex. So what you must have been doing over here, you just have interexchanged the position of ligands between these two complexes. आपने क्या किया यहाँ पे? You just have brought ammonia to the place of oxalate and vice versa. As a result of which, the combination of the central atom and the ligands have been changed. This kind of isomerism, in which you consider two complexes and you interexchange the position of the ligands in both the complexes, is called as coordination isomerism. So basically, coordination isomerism is a phenomena in which you are exchanging the place or the position of the ligands from their original complex to the adjacent complex. So due to this interexchange, what happens? You will be having a new complex arranged. You will be having a new complex formed. So these complexes, when you observe overall, the composition is same. In these two complexes all together, you are having 1 cobalt, 1 chromium, 6 ammonia and 3 oxalate. And even in set 2, you are having 1 cobalt, 1 chromium, 3 oxalates and 6 ammonia. Only their position have changed, that's it. So if you are changing the position of the constituents within this coordination entity, you call it as coordination isomerism. And these isomers which are differing from each other with respect to their position of the ligands and the central atom are called as coordination isomers. So in coordination isomers, the compounds containing complex anionic and cationic parts can be thought of as occurring by interexchange of some ligands. You can interexchange the position of some ligands or all the ligands, right? So this is what is coordination isomerism. In a brief manner, we are talking about coordination isomerism, which is a type of structural isomerism, and this isomerism involves interexchange in the position of the ligands between two adjacent complexes. Due to this interexchange in the position of the ligands, you are going to produce new set of complexes, and these two sets together are called as coordination isomers. Coordination isomers, and these coordination isomers differ from each other with respect to the composition of coordination sphere. So the difference is the composition of the coordination sphere between these two isomers that you see. All right, I hope this is clear. In case of any doubts, please let me know in the comment sections below, and let us now move on to the next type of structural isomerism called ionization isomerism. So what is ionization isomerism? When you look at the term ionization, you understand you're talking about breaking the complex and ionizing it. If you are having any complex compound or a coordination compound, and if you are subjecting this to ionization, this leads to formation of a ion, which is nothing but the coordination sphere, and along with that, whatever was primary valency, this primary valency will get separated in form of a counter ion. In case the complex ion is having a positive charge, this primary valency will have negative charge. In case the complex ion is having negative charge, the primary valency will have a positive charge. Just for example, let us observe the first complex that you see over here. You're talking about a complex of platinum, and if you ionize this, what would you acquire? If you ionize this, whatever you have here in primary valency will get separated, NO2 minus, and the remaining complex will exist as a cation, NH3 taken 3 times, and here is a cationic charge. The ionization of a complex leads to formation of resulting cations and anions. The entire square bracket part will remain as one ion, and whatever you have out of the square bracket will remain as another ion. Now the charge can be plus or minus, it depends upon the oxidation state of the central atom. Alright, now in example 1 you have seen the ions that are formed. Observe example 2 also and see the ions that are possibly formed from this example. You have Br acting as primary valency, so bromide ion is produced. And on the other hand, the remaining complex, which is PtNO2 and NH3 taken how many times? 3 times, is acting as a complex. Because you have bromide being negative, complex will have a positive charge. So even here you have 2 ions produced, bromide ion and the remaining complex acting as cation. In the first case, what do you have? In first case, you have nitrate ion and entire complex acting as a cation. Now observe the composition of both of these complexes. What do you have in complex number 1 and in complex number 2? In complex number 1 I have a platinum, so I have it in complex number 2 as well. In complex number 1 I have 3 ammonia ligands and I have it in second complex as well. In complex number 1 I was having bromine acting as a secondary valency. But in complex number 2, nitro group, NO2 group is acting as secondary valency. This is the difference. In complex number 1, NO2 group is acting as primary valency. It was out of the complex, and in complex number 2, it is bromine acting as the primary valency. So only difference between both of these complexes is position of bromine and NO2. The remaining composition is same. They have same number of platinums, they have same number of bromine, NO2 and ammonia groups. The only difference is the position. The position of these groups is different. And now what happens due to this difference? Due to difference in the position of these two groups, the ions that are produced are different, isn't it? In first case, when we ionized the complex, I had nitrate ion produce NO2 minus, and in second case when I have done this, I have a bromide ion produced Br minus. So the ions that are produced are different due to the difference in the position of these two molecules. So now these two structures that you see here, structure number 1 and structure number 2, these two structures are considered as ionization isomers. But why? Because their formula is same. These are the ones which contain the same formula or same molecular formula. But the difference between both of them is the produced after ionization. The ions produced after ionizing the complex is the point of difference. If ions produced are different, then you call those isomers as ionization isomers. In simple language, ionization isomerism is a phenomena in which two complexes have the same molecular formula, but they will be having a difference with respect to the ions produced after ionization. If the ions produced are different, you call those two structures as ionization isomers. And keep one point in mind, it's not necessary that all the complexes exhibit ionization isomerism. There are some complexes which do not exhibit this isomerism. There are some complexes जिनके पास प्राइमरी वैलेंसी होती ही नहीं है, वो complexes में ये वाला isomerism दिखता नहीं है. ठीक है? I hope you understood this. Let's move on to the next type of isomerism, and you know what you have to do in case of any doubts. Put down your doubts in the comment section below. Moving on to the third type of structural isomerism, which is called hydrate isomerism. इसका दूसरा भी नाम है. This also can be called as solvate isomerism. This also can be called as solvate isomerism. So the term hydrate or solvate is trying to represent presence of H2O molecules in the complex. So this kind of isomerism only occurs when you are having H2O species in the complex acting as either primary valency or as secondary valency. If you don't have H2O, you can't expect this kind of isomerism. So this isomerism involves interexchange in the position of H2O units. For better understanding, let us start with an example. Observe structure number 1. It's a chromium complex where H2O, there are 4 ligands and H2O acting as primary valency as well. 2 molecules of H2O acting as primary valency. And now observe structure number 2. In structure number 2, what do you have? You have 5 H2O units acting as ligands and 1 H2O unit acting as primary valency. Now you observe the difference between structure 1 and structure 2. Structure 1 has 1 chromium, so is structure 2. Structure 1 has totally 3 chlorines, so is structure 2. Structure 1 has 6 molecules of water, so is structure 2. When you look at the overall composition of structure 1 and structure 2, you get to see it to be same. It overall has 1 chromium, 3 chlorines and 6 water molecules. Then what is the difference between both of them? The position of water molecules. In the first structure, there are only 4 water molecules in the square bracket in the coordination entity. But in the second structure, there are 5 water molecules. Then what might have happened? 1 chlorine is being sent out of the coordination sphere and that chlorine's position is exchanged with the position of water. Because 1 chlorine is removed from coordination sphere, you have only 1 chlorine in the sphere now, but you have 5 water molecules. And if you observe structure number 3, you'll see the process continuing further. You have exchanged the remaining chlorine's position also with the water molecules position, resulting in existence of 6 water molecules in the coordination sphere and 3 chlorines out of the coordination sphere. So when you look at these 3 structures, they do have the same formula. There's no difference in the formula, but only the point of difference between them is the position of the H2O molecules. H2O molecules, how many ever you have in the first structure, is not equal to that of second structure and that of third structure. So the number of H2O molecules in the coordination sphere is what is changing. And this phenomena where the molecular formula of the complex is same but the position of H2O is not same. This phenomena is called as hydrate isomerism, or you also can call it as solvate isomerism. And these structures which are differing from each other with respect to the position of H2O are called as hydrate isomers or solvate isomers. But remember, this is a special type of ionization isomerism, but then this is observed only when the complex is having water. If the complex that you are talking about is not having any H2O molecules, this hydrate or solvate isomerism doesn't exist. And I also have included a few colors over here because colors of the complex compounds is an important concept. With a change in the position of H2O groups from secondary valency to primary or vice versa, the color of the complexes also will change, right? You got to learn the colors as well. So this is the third type of structural isomerism. Now let's move on to the fourth type of structural isomerism, which is linkage isomerism. So in case of linkage isomerism, the basic point is about the link or the bond between the central atom or central metal atom and the ligand. We know that the central metal atom and ligand are chemically combined with each other. Ligand donates a pair of electrons to the central metal in order to make this bond, right? So now the point is how exactly the ligand is connected to central atom. For that to be understood, you need to recap on one point about the types of the ligands. There are different types of ligands called monodentate, bidentate, polydentate, ambidentate, chelating agents, etc. I hope you're clear about the terminology. In case you are not clear about it, you can also go through this terminology from NCERT textbook, Coordination Compounds chapter. But anyway, for now, we are bothered about ambidentate ligands. Ambidentate ligands are those ligands where the ligand is diatomic by nature or maybe polyatomic by nature. The ligand has got at least 2 or more than 2 atoms in its structure, and it have capacity of acting, or it have capacity of more than 1 atoms of its structure acting as a donor. Say for example, I'm talking about NO2 minus, NO2 minus. So in this NO2 minus, when I check the structure, this is how NO2 minus looks like. And in this structure, nitrogen has got a lone pair of electrons here. And I can also write the structure in a slightly different manner, and that different manner would be nitrogen having a double bond with first oxygen atom, and with the second oxygen atom, nitrogen having a dative bond by donating its own lone pair of electrons. And in that case, this oxygen that you see here will be having 3 lone pair of electrons. And now because nitrogen does not have lone pair of electrons in this case, the lone pair of oxygen can be donated. So if you observe NO2 minus acting as a ligand, there are two possibilities. If the structure is structure 1 that you see here, nitrogen can act as the donor of lone pair. If the structure of NO2 minus is type 2 as you see here, oxygen can act as the donor of lone pair. So you're talking about a diatomic or polyatomic ligand, and in this diatomic or polyatomic ligand that you have, there is possibility that more than one atoms act as a donor. Either nitrogen can act as a donor or oxygen can act as a donor. In some cases, nitrogen might be directly connected to the central atom. In some cases, oxygen might be directly connected to central atom. This kind of ligands are called as ambidentate ligands. We call them as ambidentate ligands. So when you have such ambidentate ligands, there are two ways that the ligand can get connected to the central atom. For example, if I'm talking about NO2 in a complex form, say let's take complex of copper. So copper acting as the central atom. There are 5 ammonia ligands, but then that's not the point. The point is the other ligand we have here, which is NO2. In some cases, oxygen might be connected to cobalt and you write it as ONO. And in some cases, maybe nitrogen is connected to the central atom and you would write it as NO2. So what is the difference between structure 1 and structure 2? The difference between them is the formula is same, but then the difference between them is the way one of the ligands is connected to central atom. The way in which the ligand is connected to the central metal atom or central metal is different. So this phenomenon in which the molecular formula of the complex is same, but then the way with which or the atom through which the ligand is connected to the central atom is different, this phenomenon is called as linkage isomerism. And these two structures are called as linkage isomers. But remember, linkage isomerism is only and only seen when you have ambidentate ligands. This is possible with NO2 minus. This is also possible with SCN minus. This is minus. It has to be in the superscript here. SCN minus, nitrogen can act as the donor or sulfur also can act as the donor over here. Ambidentate ligands can exhibit this linkage isomerism. And also remember, the ligand should be at least diatomic, or it can be triatomic, tetraatomic, or it can go to polyatomic. Monoatomic ligands cannot do this. So this is the fourth type of structural isomerism. Now let us quickly go back and check what are we talking about. We are working on isomerism of coordination compounds, and this isomerism of coordination compounds can be of two types: structural isomerism and stereoisomerism. Structural isomerism is further classified into 4 types: linkage isomerism, coordination isomerism, ionization isomerism, solvate or hydrate isomerism. In all these 4 isomerisms, the molecular formula of the complexes are same. The molecular formula is same, but then the way through which the ligand is connected to central metal is different. All right. So the point of difference in the linkage isomerism is the way through which ligand and central atom are connected. If the first atom of ligand is connecting or acting as a donor, or if the second atom of ligand is acting as a donor, is what is difference here. And in case of coordination isomerism, again the molecular formula of isomers is same, but then you will be interexchanging the position of the ligands between 2 complexes that you have. So the difference over here is the position of ligands between 2 complexes that you are comparing. And the next one is ionization isomerism. Here also the molecular formula of the isomers is same, but then the ions that are produced after putting it into water is different. And solvate isomerism, molecular formula of the isomers is same, but then the number of water molecules or the position of water molecules within the complex and out of the complex, like within the square brackets of the complex and out of the square brackets of the complex, is different. All right, so this is what is about structural isomerism in complex compounds. So now we will be understanding the stereoisomerism, but not in this video. This video already has been pretty long. So we'll talk about stereoisomerism in part 2 of this video. Alright. So I'll see you in that video. In case you have any doubts about structural isomerism, you can always ask me in the comments below.